All right, so let's continue as we begin to look at motion in two dimensions under a constant force. So what I'm going to be looking at now is, of course, I've said to you before that this motion is referred to as projectile motion, meaning that the particle is moving freely in air. So what we want to look at in this section now is horizontal projection from the top of an elevation. So we have already agreed that we are looking at the particle is moving under the constant force, which in this case the force of gravity. So air resistance is negligible. So if a particle is projected horizontally from the top of an elevation with the velocity u, the particle moves forward. The particle moves forward and also downwards. So if a particle is projected horizontally with the velocity u, the particle moves forward and also downwards. So we can say that the motion of the particle is in two dimensions. It's covering motion along the vertical, which is vertically downwards, and motion along the what? Horizontal. So that is the horizontal distance covered x, vertical displacement downwards h. So the first thing we see in this motion here is that if the particle is projected horizontally, at the point of projection, the motion is in one dimension. That means that the motion is only along the horizontal. The vertical component of the velocity of projection at the point of projection is therefore zero. So we can say that at the point of projection, the vertical component of velocity is zero. So we can say that the velocity of the motion is in one dimension, which is along the what? Horizontal. That's the first thing to note. So in this case, uy is zero. Now, of course, we know that since the particle is moving vertically downwards, the direction of the acceleration, we can therefore, since the particle is moving vertically what? Downward, we can just be interested, we can therefore just emphasize the magnitude of the component of the motion along the vertical, because we know that already the direction of the motion is known. Okay? Hence, we only solve for the magnitude of the component of the motion, along the vertical. I'm going to explain this to you in greater detail. So all the equations that we've talked about previously, they are still applicable here, but the equations have now been simplified. For example, using the equation v is equal to u plus at, the vertical velocity at time t, you know that uy is zero. The acceleration along the vertical, so you should know that this becomes what we know before is that this vy becomes uy minus gt, but we know that uy is zero, so vy is equal to minus gt. This minus gt basically means the direction, is representing the direction of the vertical velocity. The vertical velocity is directed vertically downwards, and already we know it, so we are not solving for direction. So I can just say that the magnitude of the vertical velocity is equal to gt. The same thing, the velocity along the horizontal, vx is equal to ux, and ux is u. Then also, using s is equal to ut plus half at squared, the vertical height h at time t becomes uyt minus half gt squared. We know that uy is equal to what? 0. So h becomes what? Minus what? Half gt squared. This negative there represents the magnitude because a vector quantity, meaning that the particle is moving to an elevation h below the level of projection. So I can just say that the magnitude of the vertical height becomes what? Half gt squared. Then the horizontal displacement cover x becomes what? uxt. And of course, you know that ux is the velocity of projection, which is u. So the horizontal displacement x becomes what? Ut. Then using v squared is equal to u squared plus 2as. The vertical velocity vi squared becomes what? Uy squared minus 2gh. And of course, in this case, don't forget that h is definitely minus h. Or even if I don't do it like that, by the time you square that one, the magnitude of the vertical velocity squared here will just be equal to what? 2gh. If I want to explain this in another light, I can just say that that means I'm solving for this and know this. So uy is 0, h is minus h there. So vy squared becomes minus 2g minus h, which is basically 2gh. So the v squared, the square of the vertical velocity at a height h is just giving us 2gh. So these are the equations that we require in order to describe the motion of this particle in a given position. So for example, let's say that, let's take a question now. Let's take a question. So I'm just going to clean this in order to write my question. A particle is projected. A particle is projected at an elevation of 50 meters at a velocity of a particle is projected horizontally from the top of an elevation, 50 meters high, at a velocity of 20 meters per second. Okay? Determine air resistance is negligible. Air resistance is negligible. As shown below. So here we have a case in which the particle was projected horizontally from the top of an elevation 15 meters high at a velocity of 20 meters per second. So the particle moves forward and downward. So I have this. This vertical height is 15 meters. So that is the diagram describing the problem. So determine, number one, time taken for particle to reach the ground. Two, horizontal distance covered by the particle at that time, at that time, which simply means we are referring to 1. Okay, then the next one, magnitude of the resultant velocity at the point of striking the ground. At the point of striking the ground. Resultant displacement of magnitude of the resultant displacement when the particle reached the ground. Okay, so we can start solving now. The first one says, determine the time taken for the particle to reach the ground. So we said here, a particle is projected horizontally from the top of an elevation 15 meters high. At the velocity of 20 meters per second, air resistance is negligible. That means the particle is moving freely under gravity, as shown below. Determine 1. Time taken for the particle to reach the ground. RI, horizontal distance covered by the particle at that time. RRI, magnitude of the resultant velocity at the point of striking the ground. IV, which is 4. Magnitude of the displacement when the particle reaches the ground. So the first one is this. When the particle reaches the ground, what we can deduce is that it has covered the vertical height of 15 meters. So I can use this equation, the magnitude of the height h, remember we said is given as what? Half gt squared. So 15 meters is equal to half times 9.81 times t squared. So 30, t becomes equal to square root of 2 times 15, 30 over 9.81. You make that the subject of formula. And without much ado, you just bring out your calculator. You just go, look at your calculator there. You have square root of 30 divided by 9.81. That will give you t. T will be equal to 1.749 seconds, which you can approximate to two square figures as 1.7 seconds. Next question. Horizontal distance covered by the particle at that instance. Horizontal distance covered by the particle when it reaches the ground, x is equal to what? uxt. And don't forget that ux is g. So you have ut. So x becomes u. What is u? U in this question is 20. The time taken for it to reach the ground is 1.7 approximately. So this becomes 17 times 2. This becomes 34 meters approximately. Okay. Mark the horizontal velocity when it reaches the ground. That is the third one. So v becomes square root of vy squared plus vx squared. Don't forget that vy is equal to gt. That is the magnitude. So this becomes 9.81 times 1.7 approximately. So this basically will give you 9.81 times 1.7, which is 16.68. So Vy is equal to Gt, which is basically 9.81 times 1.7. And this Vy is equal to 16.68. So V becomes square root of Vy is 16.68 squared plus Vx. Vx is Ux, which is the same thing as U. Because at the point of projection, the velocity is only one direction. That becomes 20 squared. So V becomes, you use your calculator again quickly. So that becomes square root of 16.68 squared plus 20 squared. That will give you 26.04. 26.04 meters per second. So I can round up that Let me clean this diagram now, because already, or if I'm not cleaning the diagram, let me just continue. Let me clean the question. You can always refer to the question. So, because I want everything to be on a single solve. So V becomes 26.04 meters per second. So the next one, there's a magnitude of the resultant velocity, magnitude of the resultant displacement when the particle reaches the ground. That means particle projected from point P, from point O is now at point P. This is the resultant displacement. From here to here, we calculated it to be 34 meters. And this 17 meters. So it's a right angle triangle. The two adjacent sides are 15 meters, 34 meters. So with that, you can find that OP becomes square root of h squared plus x squared. So OP becomes square root of h is 15 squared plus 34 squared. And when you do that, without much ado, you're going to get square root of 15 squared plus 34 squared. And OP, resultant displacement of OP will just give you 37.16 meters, which is approximately in two square figures, 37 meters. Alright. So that is that. That is that. So we have concluded motions in 2 dimensions according to the specifications of this syllabus. Okay? So with that, you should be able to solve problems effectively when it comes to motion in 2 dimensions. And that basically wrap up kinematics. Remember we said at the beginning that kinematics is a mathematical description of motion using equations and graph. So we have described the graphical illustrations of motion. We have also described motion using equations, and we have also looked at motion in 2 dimensions. So that's that. So basically we have defined all these things before, and the reason why the equations are like that. So the only thing we just did there is to just use these questions to just describe the problem.